Hello everyone, welcome to Sunya IAS and welcome to lecture number 12 of Modern Algebra, Mathematics Optional UPSC CSE, which is asked in your paper 2 section 8. So in the last lecture, we were doing normal subgroups, right? So the only group for which the normal subgroups were not discussed was SN, right? And also I gave you a bit of intro or introduction for your quotient group, right? So let me just give you a quick recap. What happens is if you take any group, right? And naturally there is going to be some subgroup, all right, that can be the group itself or there can be a proper subgroup, right? So if there is a group and if you are making cosets with that subgroup, so if every left coset is equals to right coset, then that subgroup forms a normal subgroup, right? Then if there is a normal subgroup inside the group that we are talking about, then the set of all those cosets, okay, the collection of all the cosets of the normal subgroup forms a group that is known as your quotient group, right? Now, so this marks the start of your unit number 10, that is your quotient groups, right? Also, when we saw one example that we saw, that was set of integers, right? And what we did was we partitioned the set into remainder sets, right? So there were 5 sets which later on, at first we were calling them remainder sets, right? And then later on they took the form of the cosets only, right? So which means nothing but that this consists of numbers which leave a remainder 3 when we divide the integers in the set or in the group Z. They leave a remainder of 3 when they are divided by 5, and here they leave a remainder 4, here they leave a remainder 2, 1 and 0, right? We were calling them remainder sets, right? But later on we saw that these were nothing but cosets with respect to the group that is your 5Z, right? Now since all the cosets formed with respect to this subgroup are going to be, all the left cosets and the right cosets are going to be equal, that's why this implies that H is normal, right? So if H is a normal subgroup, then the collection of all these cosets forms a group itself, right? Now what happens is the group with respect to which we are forming the cosets is the identity element, and then obviously आपका closure and associativity वो सब follow हो जाता है, that's not a problem. But the thing is, main thing is that there exists inverse as well, right? आप ये देखो 5k plus 1 and 5k plus 4 को if you add, you get the identity element, and 5k plus 2 and 5k plus 3 if you add all the subsequent elements you add of these cosets, you are getting again the identity element of this group, where the identity element is in itself a subgroup, that is your H equals to 5Z. Clear? So what happens is हम इसको quotient group कहते हैं, right? So let's say आपका it is called quotient group also, right? And also it is known as factor group, right? Why do we call it? Because of the representation of. So if you have a group G, okay, and if you have a subgroup that is normal with respect to which you are forming the cosets, which of whose collection forms a quotient group, then you just divide by that subgroup, and this is known as your factor group. Yeah, so it is a collection of cosets, right? Uska definition bhi usi tarike se likh, right? So let's write the proper definition for your quotient group. Let G be a group and H be a normal subgroup of, right? This implies that the collection of all cosets of H in G forms a group itself, group itself known as quotient, quotient, or you can say factor, right? Now, अब चीज़ों को रटना नहीं है, right? अब we are at a point in group theory or modern algebra, if you can say, that you are not supposed to memorize stuff, है ना? Memorization वाला stuff was over like in the 9th or 10th lecture, ठीक है? Now from here onwards, अभी एक आधा दो lectures में I think we will be finishing up with group theory. Also we are going to take up PYQs as well, so it might take a bit longer to complete group theory, and then we'll be completing your ring theory, right? So we are at a point where you are not supposed to memorize stuff, right? अगर आप अब रटने लग गए, if you are trying to mug up things, what will happen? You will end up getting confused, right? So you have the definition. अभी इतना elaborate example से you know what is a quotient group. So try and write the definition of the group by yourself first. ठीक है? Pause the video here, or you can just follow along, right? So we know that we have a group G, and we need a subgroup by which we are dividing. Here we are not just exactly dividing, it is just a way of representing the group, right? And it is a collection of what? It is a collection of cosets. So the elements are going to be of the form HA, right? Why? Because H is the normal subgroup that we are using to make the cosets, right? And A is the elements of, A are the elements of the group itself, right? Also we know that कि आपको पता है कि आप यहाँ पे भले ही A belongs to G ले लोगे, but the number of cosets are going to be limited or distinct, right? So where A belongs to, right? And this equals to AH as well, where A belongs to, right? Why? Why? Since H is a normal subgroup all, or you can just write it in the form of note that XH equals to HX for all X belongs, right? Now, अब हमने ये तो देख लिया that this is forming what? This is forming a group, right? So if it is forming a group, then we need to prove that a quotient group, the collection of all cosets of a normal subgroup in G, forms a group, right? This is the most easy part, right? Why? Because this we have been doing from like since day one, since class 1. Prove that G by H, the quotient group, or by H equals to HA, where A belongs to G, forms a group, right? Now how will we prove it? Simple. First step is what? We need to prove the closure. First one is your closure property. So for closure property, what do you need? You need two elements. That means you need two cosets of the set by H, right? So let HA and HB belongs to, right? कुछ भी fancy नहीं है. We are just using what we have already been doing for so many lectures. बस हमने क्या किया? दो elements उठाए, right? आप जैसे जैसे आगे चलोगे, you will understand very easy. Also, ठीक है, we don't need to write anything. So what are we doing? अच्छा, one more thing. Forms a group, self, no, factor group, and just add one point here. Under coset multiplication. Okay? अगर आप ग्रुप डिफाइन कर रहे हो तो आपको बाइनरी ऑपरेशन भी डिफाइन करना पड़ेगा. So the binary operation is your under coset multiplication, right? And coset multiplication पे we have done n number of problems, right? Now forms a group under All right. Now HA dot HB equals to what? Ab see, can I write it as H AH B? Then I can write it as H HA. Why? Because AH equals to HA. Why? H is normal, right? Now this implies that HHAB. Okay. So this implies that HAB will get HH is equals to H only. Okay, we have done this. We have already proved this, right? So this is giving us another coset, right? Now A comma B belongs to G. This implies that AB belongs to G. Why? Because G is also a group, right? Any problem in that? So since AB is an element of G and we are getting a coset with respect to this element, so this is also going to be a coset, right? So this implies that HAB belongs to by, right? This implies that closure property satisfies, right? All right. The second one is your associate. Now for associativity, you need three elements. That means you need three cosets. HA, HB, HC belongs to E by H are the three elements that we have taken from the quotient set, we'll call it at the moment, right? So now I want to check if the order of coset multiplication matters or not. ठीक है, इसको हम एक तरफ से सॉल्व करते हैं and we'll end it up on the दूसरा side where HA and HB are going to be operated, right? HA is outside. Here we are going to follow the same pattern. So what is going to happen? HB give you HA, HB, right? Again you're going to apply the same thing, that is going to be H, right? Right? If I can write it like this, I can also split it, right? Again I can write it like this. Let's say HA, HB. Okay, let's take up from the left hand side only. Okay, not to complicate things. HA and HB will be solving first. Here we'll get HAB. This will give you HAB, HC. I guess we did one theorem as well, na? Where we can write HAHB is equals to HAB, right? ठीक है, वो भी यूज कर सकते थे, कोई बात नहीं. So associativity also holds here, right? Now for the next part we need the identity. Just think about it. Think about this example that we did here. What was the identity element? Identity element was if you multiply by that element, you're going to get the set again. If I multiply 5k plus 2 by 5k, that means if I'm adding these two cosets, again I'm going to get 5k plus. So for a quotient group, the H group with respect to which you are forming the cosets is the identity element, right? So H belongs to by H such that for HA belongs to G by H, where A belongs to G, HA dot H equals to HA, that is your HA, right? This implies that H equals to the identity element such that EA equals to AE equals to A for all A belongs to, or what we can do is we can write the element as it is, such that HA dot E equals to E dot HA equals to HA for all HA belongs to, right? Now finally we have to do the inverse. Now think about it. I need for HA some element here, so that if I multiply it by that element, I'm going to get the identity element, right? So obviously, can I write this as HE, right? So basically I need an element here for which I'm going to get identity element on the right hand side, right? Which is going to be your HA inverse. Why? Because A is going to belong to G, then that means A inverse is also going to belong to G, right? Now let A belongs to G implies that A inverse belongs to G as well, right? This implies that HA belongs to by H and HA inverse belongs to by H, and HA dot HA inverse equals to HAA inverse equals to HE, right? Which is the identity element of by H, right? So there exists HA inverse for all HA belongs to E by H, such that HA inverse equals to HA inverse HA equals to, right? So this implies that the inverse element also exists. यहाँ पे आप नीचे लिख सकते हो that quotient group forms a, right? Okay. Now after this we have, if H is a normal subgroup of a finite subgroup, the normal subgroup of a finite group is okay, then order of G by H, right? अब हम एक ग्रुप की बात कर रहे हैं, so उसकी कार्डिनलिटी के बारे में भी we are going to talk. So for a factor group आपको कुछ नहीं करना है, basically it is the number of, and how do we find the number of cosets? It is the index of that subgroup. Index of the subgroup is equals to order of G divided by order of, right? इसमें कुछ बहुत ज़्यादा complicated proof नहीं, you're just supposed to write what I just said. Let G be a group and H a normal so order of E by H equals to number of elements in G by H, right? Which is equals to number of cosets in G by H, right? If number of cosets are to be calculated in G by H, what do I need? I need the index of H, which is nothing but order of G divided by order of, right? This is exactly what we wanted to, right? That order of G by H is equal to order of G divided by order of H, right? अब यहाँ से आपको इससे भी अंदाजा पड़ जाएगा कि आपके पास कितने नॉर्मल सब ग्रुप्स हैं, है ना, एंड व्हाट काइंड ऑफ फैक्टर ग्रुप्स आर पॉसिबल, राइट? अब आप ये नहीं कह सकते, अभी नहीं कह सकते दैट G by H इज अ सब ग्रुप, राइट? वाई? बिकॉज आपका ग्रुप एक कलेक्शन ऑफ एलिमेंट्स है, राइट? G by H कलेक्शन ऑफ सबसेट्स है, कलेक्शन ऑफ सेट्स है, right? So it is a totally different, right? Okay, moving on, that every quotient group and of an abelian group is abelian. Very easy to prove. क्या करना है? Basically we want to show, आपके दिमाग में सबसे पहले क्या आता है? क्वोशंट ग्रुप के 2 एलिमेंट्स. जब भी आप नॉर्मल ग्रुप की बात करते थे, यू नीड 2 एलिमेंट्स, राइट? एंड टू प्रूव दैट दिस ग्रुप इज abelian, what do you need? You need to prove that AB equals to BA for all A comma B belongs to G, right? But now I'm talking about a quotient group. So what are the elements like HA, HB? So I need to prove that HB equals, sorry, HA HB is equals to HB HA, right? Okay. I guess अभी तक समझ में आ गया होगा. It is going to be very simple to prove it. Let G be a group and H a, or we can write here, we're talking about an abelian, be an abelian group and H be a subgroup. Okay. Now we do not need to specify that H is going to be a normal subgroup. Why? Because for a abelian group, all the subgroups are आपका normal subgroup, right? So now we need to prove, we need to show that E by H is abelian. Let HA, यहाँ पे you can write the definition of GH as well, G by H as well, लिख ही लेते हैं. So G by H is equal to HA, A belongs, right? Let HA comma HB belongs to G by H, right? So HA dot HB equals to HAB. Okay, this we have already proved n number of times, right? But can I write HAB as HBA? Why? Because A and B belong to G and G is abelian, right? So this is going to be HB dot HA, right? And this is true for HA dot HB equals to HB HA for all HA comma HB belongs to by implies that by H of B abelian or by H is, यहाँ से we can write a result that factor group of abelian group is abelian, right? But converse need not be true, that if a factor group is abelian, that makes आपका the group also be. This is not going to be true. इसके examples आप बाद में देखोगे. अभी के लिए just write that factor group of a abelian group forms an abelian. Yeah. Okay. So similarly, we are going to show that every quotient group of a cyclic group is going to be cyclic, right? Let be a cyclic, right? And H be a subgroup of G by H is a quotient group here of the form HA and A belongs to, right? Now we need to show that G by H is a cyclic group. Now if you want to show that a group is a cyclic group, I need to show that all the elements of that group can be generated by one single element. Here, first let's look over how our G is going to look, right? Now since G is cyclic, let there exist A belongs to G such that G is generated by A, right? So this implies that G is going to look like something like A raised to the power 0, A raised to the power 1, A raised to the power 2. Okay, wait. a raised to the power 1 cube till a raised to the power n minus 1, which is equal, right? So these are the elements that are going to be the part of G, right? Now, whatever the cosets are being generated, they are being generated by these elements only, right? So just consider for a moment, consider a raised to the power n, and or just write, consider the coset generated by h a raised to the power n, right? This is going to be a coset h a raised to the power n, right? Now can I write it as h a n times, right? Any problem in that, right? आराम से लिख सकते हैं a को expand करके. Now we know that h a dot h b equals to h a b, right, for a normal subgroup. So can I write it as h a n times, right? Now this can be written as h a raised to the power n, and this, it is equals to what? Now what does this statement show us? That every coset of the form a raised to the power h a raised to the power n can be generated with the help of the set, with the help of the element of G by H, that is your H, right? So there exists H a belongs to G, which can generate the group by, right? So this implies that G by H is, if you have space, just write here that the quotient group of a cyclic group is again a cyclic, right? Chalo, moving on, I guess. Okay, so now अभी तक हमने जितने भी questions करे ना in the normal subgroup वाला part, right? तब तक आप सारी चीज़ें आप देख चुके किस तरीके से evaluate करनी होती है, right? So it's very important that you keep applying them. So I have given some like homework questions to try them. You don't get them, you're going to get them in the notes, ठीक है? इनके solutions यहाँ पे available हैं, but I would really suggest that you try them, ठीक है? Okay, क्योंकि आपका collection of all 2 order elements के सब group पे काम हम पहले कर चुके हैं, right? Also whatever the elements यहाँ पे इस तरीके के elements पे भी we have worked before, so I don't think it will be very difficult for you to, right? Okay, now अब क्या है ना, that we took one example of z being the group, z plus being the group, and 5z being the subgroup, right? But it's important that you take more examples, right? So we are going to just do some of the examples of the groups that we have been doing till now. Okay, so first I guess we'll take q4 by z of q, okay, where q4 is plus minus 1 plus minus I plus minus and z of q4 is what? Center of group, collection of all elements which commute with all the elements, right? So minus 1 and 1 are the 2 elements which commute with all the elements of 4. Now we want to see that what are the cosets lying in it, right? And if it is forming a group. Now see, definitely it is going to form a group, but we want to see what are the elements, what do the elements look, right? So first of all, let's talk about the order, because order आएगा तभी we'll be able to see कि ये वाला जो group है, ultimately it is a group, right? It is going to be isomorphic to some group, right? अब देखो, what is order of q4? Order of z, order of zq4 is 2. Order of the factor group q4 upon zq4 is going to be, right? This implies that we have 2 isomorphisms possible. That is either Z4 or have Z2 cross Z2, right? So we are supposed to see कि आपके पास order of elements क्या मिल रहा है. देखो यहाँ पे what are the orders possible? 1, 2 and but यहाँ पे only the order possible is 1 and 2. So we are going to just look कि इसके elements में किस तरीके के orders हैं. उसके basis पे we'll be able to tell that what is going to be the isomorphic group, this factor group, right? All right. So first let's take I guess one, that is the identity element, right? So 1 dot ZQ4 is going to be equals to ZQ4 only, right? So order of 1 dot ZQ is going to be what? Is going to be 1, right? Because coset का identity element क्या है? The coset, the subgroup itself, right? So what is the subgroup? ZQ. Similarly, I can say कि -1 से जो coset बनेगा that is also going to be, right? अब देखो order of let's say I dot ZQ. अब इसको calculate करने के लिए simply just treat iota ZQ4 as one element, right? So what am I going to do? I am going to check for it. आप क्या करते हो? आप order check करना चाहते हो तो आप पहले a square check करते हो, a cube check करते हो, a raised to the power 4 check करते हो, right? So I'm going to check for power 2. So this is going to give me what? I square and Z cube. H square is again h is equals to h. तो यहाँ पे इसका कोई point नहीं है इसको लिखने का, right? So I square is what? -1, which is a part of ZQ4 only, right? So I can submerge -1 into ZQ4, right? मतलब -1 is an element of ZQ4, so the coset generated by -1 is going to be ZQ4 itself, right? So that means the order of the element or the coset, that is your iota ZQ4, is going to be 2. Clear? Now similarly try for J. J, that means the coset generated by J. So this is going to be ZQ4. Let's try for 2. This is again going to give me Z square ZQ4 equals to -1 ZQ, which is again a part of ZQ, which is the identity element. If you find it confusing, just write it here that this is the identity element. Okay? So when I'm operating an element 2 times, I'm getting the identity element. This means order is going to be. So similarly, what is going to happen? Similarly, order of K dot ZQ will be. So now, अब आपको पता है, आपको वो ज़्यादा evaluate करने की ज़रूरत नहीं है, because -I and I generate the same cosets, -J and J generate the same cosets, and similarly K and -K also generate the same cosets, right? So we have one element of order 1 and 3 elements of order, right? अब 1 element of order 1 and 3 elements of order 2. और order क्या था आपके factor group का? 4, right? तो आपको चारों elements मिल चुके हैं, उनका order मिल चुका है, and which is similar to Z2 cross Z2 and not Z4. Clear? So this implies that G by, or right, Q4 by ZQ isomorphic to, right? अब आप ये देखो, just pay attention. इतना कॉम्प्लेक्स कॉन्सेप्ट, आप पहले ग्रुप पे आए, देन आप सब ग्रुप्स पे आए, फिर आप abelian, cyclic इन सब ग्रुप्स पे गए, देन यू टॉक्ड अबाउट कोसेट्स, देन यू टॉक्ड अबाउट नॉर्मल सब ग्रुप्स, देन यू टॉक्ड अबाउट कोशेंट ग्रुप्स. घूम फिर के आपने एक ऐसा ग्रुप बनाया इन सब कॉन्सेप्ट्स को यूज करके, which is just similar to this very simple group, that is your Z2 cross Z2. तो आपका group theory can be very confusing or technical at one point, and it can be as simple as this calculation here, that such a complex concept can be just reduced to Z2 cross. Exactly this is what the basis of abstract algebra, कि आपके पास जब higher degree के equations आते हैं, राइट, तो कैसे आप उनको इतना सिंप्लीफाई करके उनका सोल्यूशन निकाल सकते हो. So that is basically the crux of modern algebra or abstract algebra, if you want to call it that, right? Chalo. Let's take another example. Abhi we talked about Q4 and Z Q4, right? So let's talk about, अच्छा ठीक है, let's talk about आपका Z upon 6Z. See? Now we know what kind of cosets are being generated by such an element or such a factor group. Let's say you have 0 plus 6Z, then you have 1 plus 6Z, right? Then you have 2 plus 6Z, 3 plus 6Z, 4 plus 6Z, and 5 plus, right? Now अगर आप इनके ऑर्डर्स देखोगे तो ऑर्डर्स आर अगेन गोइंग टू बी आपका सिमिलर टू, या तो आप इनके ऑर्डर्स निकाल के ही देख लो, ठीक है? लेट्स से इफ यू हैव 0 प्लस 6Z, ठीक है, इफ यू ऑपरेटेड 2 टाइम्स व्हाट और 1 टाइम, you are going to get again 6Z, which is going to be the identity element, right? Now let's say we have 1 plus 6Z. So how many times do I need to operate this element again and again with itself such that this integer gets merged into 6Z? That is going to be, so this is going to give you 6 plus 6Z, which is again what? 0 plus, right? So this is the identity element. Similarly for 2 plus 6Z, so the order is going to be 3. Why? Because I need to add 3 times. I'm going to get 6 and it is going to get submerged into 6Z. Then finally 3 plus 6Z, order 2 हो जाएगा, right? अगर आप ऐसे ही करते रहोगे, so you are going to get that, you're going to see that the properties shown by the elements of this factor group are going to be similar to आपका एक cyclic group, right? अब आप ये देखो, इसको आप ऐसे भी अप्रोच करो, that order of z by 6Z equals to order of z by order of, right? But the problem is that this is infinite, right? तो हम इसको इस तरीके से अप्रोच नहीं करते, ठीक है, कि पहले आपने इंडेक्स निकाल लिया, इंडेक्स के बाद आप कर रहे हो. वाई? बिकॉज दैट इज एन इन्फिनाइट ग्रुप, राइट? आपको ऐसे ही देखना पड़ेगा दैट व्हाट आर द ऑर्डर्स ऑफ द एलिमेंट, राइट? आप जब इसको जनरलाइज करोगे, सो यू विल सी दैट z upon 6Z is going to be isomorphic to Z, right? So this gives us the result here, that is, if you take D to be your set of integers and if you are taking any subgroup of the form mz, right? So what is going to happen? The factor group Z upon mz is going to be isomorphic to Zm, right? Also note that Z is a cyclic group, right? So it is, the factor groups are also going to be cyclic. कोई भी order का आपको मिलेगा वो cyclic subgroup, right? Cyclic quotient group, right? अब यहाँ पे m is not equals to, and if m is equals to 0, then isomorphic to again Z. Alright, so this is the आपका note जिससे आपको ध्यान रखना है. This was about your infinite cyclic group, that is your Z. Now let's talk about the finite Zms that we talk about, that is your group of residues. Let's say we have Z20 upon cyclic group generated by 10, right? Since Z20 is a cyclic group, आपके सारे subgroups are going to be normal subgroups, right? So आपका cyclic group generated by 10 is also going to be a cyclic group and it is going to be a normal sub, right? Now order of the factor group is going to be what? Is 20, What is the order of the cyclic group? 10. This is 2. So order of the factor group is going to be 10, right? So there are up to isomorphisms here. Why? Because 2 divides 5 minus 1, right? So 2 up to isomorphisms are possible for the factor group. Now order of, or we should write Z20 upon 10 is isomorphic to either Z10, right, or D, right, which is a non-abelian. But the thing is that since Z20 is cyclic, Z20 is cyclic, factor group of Z20 also cyclic, right? This implies that Z20 upon the cyclic group generated by 10 is isomorphic to Z10. Yeah. Now here is an important result. अगर आपको otherwise कुछ इसमें try करना है तो आप कर लेना यहाँ पे, no problem in that. But the result is that if m divides n, then the factor group Zn upon the cyclic group generated by m is isomorphic, right? अब इसमें आपके पास homework ये है that you are supposed to check all the factor groups possible inside a cyclic group which is of the form Zm, right? तो आप पहले Z3, Z4, Z10 इनके लिए चेक करके देखो and just try to see what are the properties that are being executed by such kind of group, right? चलो, let's take another example. Are we talking about the group again here? Sure. All right. We have a question that there is one question so that order of P by ZG P is never possible. Okay, just try this question here and try to see if you can apply the concepts that we have done till now. See, order of P by ZG is given to us as P, right? So this implies that P by ZG is isomorphic to ZP, right? Since P is a prime number, right? So this implies that G is abelian. But if G is abelian, then ZG is equals to G. Then order of G by ZG is what? Equals to order of G upon order of ZG. That is going to be equals to order of G upon order of G. That is 1, which is not equals to, right? So that is why order of G by ZG is never possible a prime number. Clear? Chalo. Conjugate element baad ka hai. We are going to discuss one more group, that is your UN. Okay, you remember the group UN? Right? So the collection of all the numbers less than n, okay, and which whose GCD is equals to 1 with n. Clear? Basically the collection of all co-prime numbers to n. Clear? Now what kind of a group or what kind of a subgroup forms a normal subgroup with it? इट इज़ जस्ट फॉर नीड टू नो बेसिस, और कुछ नहीं है इसमें, ज़्यादा आपको मेहनत नहीं करनी है, इट इज़ जस्ट कि आपको पता होना चाहिए। ठीक है, तो द काइंड ऑफ ग्रुप दैट फॉर्म्स अ फैक्टर ग्रुप, और यू कैन से इट फॉर्म्स अ सब ग्रुप, पहले तो सब ग्रुप की बात करते हैं, इज योर UKN, राइट, where the elements they belong to UN, right? And what is special about them is that x minus 1, that means x congruent to 1 mod k hota hai, that means x minus 1 is divisible by your the element k, जो भी आपका यहाँ पे UKN दिया हुआ है, अभी आपको एग्जाम्पल से ज़्यादा बेटर समझ में आएगा। व्हेन इट इज़ गिवन UKN, दैट मीन्स आपने क्या करना है, जितने भी एलिमेंट्स आपके प्रेजेंट हैं UN में, राइट, यू आर सपोज टू सब्ट्रैक्ट वन फ्रॉम देम एंड यू आर सपोज टू चेक व्हाट आर द एलिमेंट्स विच आर डिविजिबल बाय दिस नंबर k. फॉर एग्जाम्पल, इफ आई टेक लेट्स से U of 21, ठीक है, सो व्हाट आर द एलिमेंट्स विच आर गोइंग टू बी को प्राइम टू 21, इट इज गोइंग टू बी 1 2 not 3 4 5, 6 is not going to be there, not 7, right, then 8 9 नहीं आएगा, 10 11 12 नहीं आएगा, 13 14 भी नहीं, 16 no, 16 17 18 no, not 18 19 and then 20, right? So these are the elements that are going to be present in U21, right? So now if I take an example, let's say U321, right? And also what is special here is that if k divides n, ठीक है, the condition is that if k divides n, then आपका ये जो ग्रुप बनता है that is आपका subgroup of UN, clear? So this is, now you have to check that amongst these elements, which are the elements from whom I'm going to subtract 1 and that is going to be divisible by 3. So the elements are going to be 4, okay, then 4 7 9, okay, then you have 13, then you have 16 and then you have 19. So these are the elements that are going to form again a group, ठीक है, ज़्यादा डिटेल्स में नहीं जाना है, you just have to understand that this is going to be a normal subgroup and the factor group is going to be isomorphic to U. Here, so here U of 21 divided by U3 of 21 is going to be isomorphic to U, right? Note. Clear? So this is the note you can write here. All right. चलो अब हम अपना सबसे फेवरेट ग्रुप के बारे में बात करेंगे, दैट इज़ योर SN ग्रुप, जिसके अभी हमने नॉर्मल सब ग्रुप्स भी डिस्कस नहीं करे हैं, राइट? So before we dive into our permutation groups, first let's talk about one question, that so that AN is a normal subgroup of S. Think about it for a second, that how can you show that AN is going to be a subgroup of a normal subgroup of SN? Subgroup है ये हमें पता है, but if it is a normal subgroup, how will we show that? We can show that by the help of index. Why? Because हमें पता है that a subgroup of index 2 is always a normal subgroup, right? So from here, order of, or I should say index of H with respect to G, that is index of AN with respect to SN, equals to order of SN upon order of, what is the order of SN? N factorial. What is the order of AN? N factorial by, this makes the order of, or the index of AN in SN equals to 2. This implies that since index of AN in G or in SN is 2, an is normal, right? Ab an is normal in Sn, right? But how will we find out that what are the normal subgroups of an? Because an itself is a group, right? And it is a very large group. We need to discuss about the elements or the types of subgroups or normal subgroups that are present in your an, right? So if you remember, still we have not discussed the subgroups of A4 or A3 for that matter. A3 तो ठीक है, उसका कुछ ज़्यादा करने का डिस्कस है नहीं. Important is your A4, right? चलो, so let's start with discussing the subgroups of A4. अब क्यों A4 डिस्कस कर रहे हैं वो आपको थोड़ी देर में समझ में आए. तो order of A4 is 4 factorial divided by 2, that is 24 divided by 2. Possible orders of subgroups equals to 1, 2, 3, 4, 6, right? 12 नहीं लिख सकते because we know that आपका it is not a cyclic group, right? Now let's start with number of, just give me a moment, number of cyclic subgroups of order 1. It is going to be pretty easy. Abhi to we know how to calculate it, right? Now number of cyclic subgroup of order 2. Now for that we need number of elements of order 2, right, upon phi of 2. Now do we remember how do we calculate number of elements? The partition of 4 is going to be 4 plus 1 plus 1, not 2 plus 1, plus 2, and 2 plus 1 plus 1, and finally 1 plus 1 plus 1, right? So the only possibilities where we can find elements of order 2, they are going to be here, because the LCM is going to come 2, and here, right? So the total number of elements of order 2 are going to be 4 factorial divided by 2 raised to the power 2 into 2 factorial. I hope ये सबको याद होगा. Then we need to discuss the second case as well. That is going to be your 2 into 1 square into 2 factorial divided by phi of 2, that is nothing but 1. So here we have 4, 2, so 3 will be remaining, and here we have 4, 6. So there are 9 elements of order 2, or in short we can say that there are 9 cyclic subgroups of order 2 inside A4. Clear? Now number of cyclic next up we have number of cyclic groups of order 3, right? So number of cyclic subgroups. Why am I writing cyclic? Because 2 and 3 both are prime numbers, right? Cyclic subgroups of order 3 is going to be number of elements of order 3 divided by phi of 3, right? So what is the possibility that I'm going to get an element of order 3? That is going to be just 1 from here, right? 3 and 1. Also, if you want to check कि आपका 3 cycle is going to be an even permutation or not, just understand like this. एक example ले लो, 1, 2, 3, right? And 4 is going to be given with 4 only, right? So what is the representation in terms of transpositions? 1, 3 and 1, 2, right? So this is even number of transpositions. So that means it is a even permutation. So it will lie in the A4 group only. Now, so how many number of elements are going to be there? 4 factorial upon 3 plus 1. So 3 into 1 into 1 factorial into 1 factorial divided by phi of. So this gives us 8 upon 2, that is, right? So there are going to be 4 subgroups of order 3 which are going to be cyclic in A4, right? Now moving on to 4. Now number of subgroups of order 4. So if there is a subgroup of order 4, that is going to be your H, and it is going to be isomorphic to either H Z4 or Z2 cross, right? But आप खुद सोचो, if there is going to be a subgroup which is going to be isomorphic to Z4, that means there is going to be an element of order, right? But if you have an element of order 4, let's say 1, 2, 3 and 4, right? So can I represent it in the form of transpositions? Yes. So it will be 1, 4, 1, 3 and 1, 2, which is odd number of transpositions, right? So an element of order 4 is not going to belong to A4, right? So this implies that if there exists a subgroup, it is going to be isomorphic to Z2 cross, right? So यहाँ पे you can write that A4 does not have elements of order, right? Chalo. So if the subgroup is isomorphic to Z2 cross Z2, that means we need one element of order 1 and 3 elements of order 2, right? अब अगर आप इसको लिख के देखोगे तो आपको याद आ जाएगा या आपको समझ में भी आ जाएगा. So if you need 3 elements, they are going to be of the form. First is going to be your identity element. Then you have 1, 2, 3, 4. Okay, so these are the product of two transpositions, right? So it is an even permutation. Then you have 1, 3, 2, 4 and finally 1, 4. You notice this is a 2 cycle, this is a 2 cycle. The LCM is 2. So order is going to be 2 only, right? I'll just write it here. The order is going to be 2. This is also of order 2 and this is of order 2, right? And these are the only elements that you're going to get. So there is going to be unique subgroup of order 4 which is going to be isomorphic to Z2 cross Z2. Clear? Chalo. Number of elements of order 2 हमारे निकले कितने थे? Number of elements of order 2, we had 9 elements, right? So there must be more. Okay. Okay, but the inverses have to lie here only, right? Okay, so this is going to be your subgroup which is going to be of order, right? Okay, give me a moment. Tiny error here. That is your this part. Why? Because we cannot consider this cycle, because this is not going to belong to this one. This is not going to belong. These elements are not going to belong in A and Y because it can be represented in the form of one transpose, right? So it is not going to be an even permutation. Only आपका यहाँ पे you have 1, 2 cycle and 1, 2 cycle, that is your product of two transpositions. This is going to lie in the even permutation group and not the elements of the form 2 plus 1 plus 1, right? So that is what I was saying कि एकदम से 9 elements if I'm getting of order 2, then cyclic subgroups are 9 and then it is exceeding the groups over there. Okay, the number of elements of order 2 are going to be 4 factorial upon 2 square into 2 factorial, right? So this is going to be 4 into 3 upon 4 into 2. So there are total 3 cyclic subgroups of order, right? And they are cyclic subgroups of order 2. That means आप एक बारी में एक 2 order का element consider करोगे and you're going to make subgroups which are going to be isomorphic to Z2, right? Okay, and the elements are of the form 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2. So these are the only 3 आपके elements of order 2 present inside the group you're alternating, right? Alternating a group of order 4, right? Okay, so where were we? So that is why we have a unique subgroup here that is going to be आपका 3 elements of order 2, and since there are only 3 elements of order 2 inside A4, this is going to be the unique here, and it is not going to be isomorphic to Z4. Now the most important part on which we have discarded our Lagrange's theorem as well. That is what? That is your subgroup of order 6, right? अब इसमें पता है बहुत ज़्यादा you don't have to get technical and all that. इसको भी हम Lagrange's theorem से ही prove करेंगे कि क्यों इसमें आपका it is not going to exist, a subgroup of order 6 is not going to exist. बनाने को आप बना दो, फिर आप उसमें अप्लाई करके देखोगे there are going to be certain nuances that are not going to get followed. But the simple crux as to why a subgroup of order 6 does not exist in AN is because, just understand it like this, that I have to take 6 elements in order to form a subgroup of order 6, right? So let's say if I take elements of order 1, 2 and 3 and 1, 2, 3 and 6 are possible, right? 6 is not possible. Why? Because it is not a cyclic subgroup, right? Now, just understand it like this, that I can take elements of order 1, 2 and then order of elements of order 3, right? What is the prime factorization of 6? It is 2 into 3, right? Now 2 divides 3 minus 1. This implies that there are 2 isomorphisms possible. One is your Z6 and second one is your S3, right? We know that it is not going to be isomorphic to Z6. That means it has to be isomorphic to S3, right? And what does our S3 look like? S3 has I 1, 2, 2, 3, 1, 3. Then you have 1, 2, 3 and 1, 3, right? So 6 elements are there, of which 1 element is of order 1, 3 elements are of order 2 and 2 elements are there of order 3, right? So similarly, if this subgroup is going to be similar to S3, then it must have 3 elements of order 2, right? And we know that exactly there are 3 elements of order 2 in A4, right? So all of them are going to be present in this subgroup if this subgroup exists and it is isomorphic to S3, right? So the elements of order 2 are going to be present inside this group or subgroup. So they are going to be 1, 2, 3, 4, 1, 3, 4 and 1, 4, right? And then you will have order of elements of order 3 as well, right? But they are not important here. So I'm just going to erase this abhi yahan pe. अब देखो क्या होगा. Now we have already seen that the collection of these elements forms a subgroup of order 4. कहाँ से? यहाँ से. That it forms a subgroup of order 4 which is isomorphic to Z2 group. Clear? Now, जो भी हम यहाँ पे collection of elements लेंगे, it is going to be a subset of A4, right? It has another subset which is in itself a group, right? If there exists a subgroup of order 6, then if there exists a subgroup of order 6, then order of that group must be divisible by order of H4. H4 कौन सा ग्रुप है? ये वाला. इसको यहाँ पे H4 का नाम दे दो या फिर H डैश नाम दे दो, कोई बात नहीं, राइट? दोबारा से समझो. I am taking this H here, right? And I'm saying that this is a subgroup of order 6 that exists inside of A4, right? I have also made one subgroup which is of order 4 and it consists of all 3 elements of order 2, right? This exact group, the elements of this exact subgroup exist in this set as well, right? So if this subgroup is forming a subgroup of order 6, then this is going to be a subgroup of it, right? And if H4 is a subgroup of this group, then it must divide the order of this group. But we know that 4 does not divide, right? बस एक सिंपल सा यही लॉजिक है. इसीलिए आपका there does not exist any subgroup of order 6 in A4, right? अब इसको आप एक प्रॉपर प्रूफ में भी लिख सकते हो. आई एम श्योर कि अभी आपको प्रॉपर मेथड यू ऑल नो हाउ टू राइट इट, राइट. आप ऐसे लिखना है यहाँ पे दैट, इसमें आप इसका नाम रख देना सम ग्रुप, और मे बी यू कैन जस्ट स्टार्ट फ्रॉम हियर. यहाँ पे आप H1 लेना, फिर यहाँ पे H2, H3, H4 हो जाएगा, एंड देन कॉल दिस वन एज H5, राइट. देन यू हैव H6 हियर. सो इफ H6 एग्जिस्ट्स, देन आप इस तरीके से प्रोसीड करना. सिंस H5 is a subset of H6, that means H5 in itself is a subgroup. So if H6 is a subgroup, then order of H5 is going to divide order of H6. But this is not possible. Why? Because 4 does not divide 6. That is why a subgroup of order 6 does not exist in A. Through this only we are able to say that converse of Lagrange's theorem is not true, right? Chalo. Now let's talk about the normal subgroups of Sn. Normal subgroup of Sn. If n is greater than equals to and n is not equals to 4, right? अगर n की वैल्यू 3 से बड़ी है एंड n is not equals to 4, मतलब हम S4 की बात नहीं कर रहे हैं यहाँ पे, then H1 equals to identity, right? Then you have H2 equals to Sn itself, right? And then you have H3 equals to An. These are the normal subgroup. So there are 3 normal subgroups in Sn when n is greater than equals to 3 and n is not equal to, right? हम देख चुके हैं why an is going to be a subgroup, a normal subgroup. Why? Because index of an is always going to be 2, right? Now अब we left one condition, that is our n is not equals to 4. Now what happens is, if n equals to 4, अब n equals to 4 means we are talking about S4, right? अब S4 के अंदर आपका A4 भी आता है. A4 के अंदर आपका एक और ऑर्डर 4 का एक सब ग्रुप आएगा, दैट इज गोइंग टू बी H5, जिसके बारे में हम अभी बात कर रहे थे, विच इज द ओनली नॉर्मल सब ग्रुप in A4 apart from in S4 apart from A4. Yeah, so this is a important distinction, I would say. You have to write it over here. If n is equals to 4, then normal subgroups of S4 are H1 equals to identity, H2 equals to S4, H3 equals to A4, and H4 equals to identity 1, 2, 3. Okay, so there are a total 4 normal subgroups of S4. That is going to be your identity, S4 itself, A4, and then H4, right? अब H4 A4 का subgroup है, that means it is going to be also a subgroup of S4. Clear? So this implies that there are 4 normal subgroups of S4, right? Now let's talk about normal subgroups of An. Same scenario, if n is greater than equals to 3 and n is not equals to 4, okay, then normal subgroups are H1 equals to identity, H2 equals to An. There are 2 normal subgroups in right? And if n is equals to 4, if n equals to 4, then you have h1 equals to identity, then h2 equals to a4, and then h3 equals to identity here 1 2. Okay. So in this case, when n equals to 4, there are 3 normal subgroups, right? Ab just understand why did we do all this mehnat, because we were studying factor groups, right? So in order to find the factor groups of Sn, we studied the subgroups of A4. Why? Because we wanted to find out a subgroup of order 4, that is your normal subgroup for A4, and also normal subgroup for S. Here, now let's talk about aapka factor groups. Should we just make some space in these pages only? Chalo, theek hai, let's do it separately. Now, factor groups of Sn, right? First one is when n is greater than equals to 3 and n is not equals to, right? So what were the normal subgroups of Sn? Only 3 normal subgroups were there, which were identity, Sn itself, and An, right? So 3 factor groups are also going to be there. That is going to be Sn upon identity, and which is going to be isomorphic to Sn. Then you have Sn upon An, which is going to be isomorphic to Z2, right? And then you have Sn upon Sn, which is going to be isomorphic to Z1. Clear? Now, if n is equals to 4, right? If n equals to 4, then you have Sn upon identity, which is going to be isomorphic to Sn, right? Then Sn upon An, which is going to be isomorphic to Z2, or we should write Z4, S4 and A4. First one is your S4 upon identity, which is isomorphic to S4. Then S4 upon A4, isomorphic to Z2, right? Then S4 upon S4, which is again isomorphic to Z1, right? Now, S4 upon H4, right? Order of S4 upon H4 is going to be order of S4 upon order of H4, which is what? This 4 factorial upon this is 6, right? So that means the factor group S4 upon H4 is either isomorphic to what? Z6, or it is isomorphic to S3, right? But it does not have any element of order 6, right? So from here we can say that S4 upon H4 is the 4th factor group which is isomorphic to, right? Not possible. Clear? Now moving on to factor groups of An. First one is if n is greater than equals to 3 and n is not equals to. So what are the normal subgroups? The normal subgroups are identity and the group itself, that is your An, right? So An upon identity, which is isomorphic to An again, right? Then you have An upon An, isomorphic to Z1, right? But if n equals to 4, then you have an upon or a4 upon identity, it is isomorphic to a4 only, right? And a4 upon a4, which is going to be isomorphic to z1. Now we know that there is another group, that is your h4, right? So what is the order of this group going to be? Order of a4 upon order of h4. So this is 12 upon 4, that is right. Now 3 के लिए आपके पास एक ही isomorphism है, that is your z3. So this implies that, or write it green on. So a4 upon h4, a4 upon h4 is going to be isomorphic to z3. Here, so you have 3 up to 3 factor groups when n is equals to 4, that is your a4, z1 and z3, right? Most important points is that there is a factor group inside or generated by s4 and h4, which is isomorphic to s3, right? And there exists a factor group inside or generated by a4, which is isomorphic to z3. The very important results, okay? आपको ये examples quote करने के लिए बहुत काम आ सकते हैं. Yeah. चलो, now let me see if we are left with any other examples or we can proceed to the next topic. Okay. So the next topic is your conjugate elements, okay? After conjugate elements, we will be studying your, then we'll be doing आपका class equations, and then we'll be jumping towards your homomorphism, right? Now why do we need conjugate elements, right? आपके पास कुछ results हैं इसके related, right? यहाँ पे if you remember, we did two things, that is your center of group and your normalizer of an element, right? Those two things are going to come in handy when we will be studying some concepts, that is your class equation and all. Abhi filhal let's focus on studying our conjugate elements. Now what are conjugate elements? I'm straightforward going to write the definition, you'll understand it. So let G be a group and A and B be two elements or be elements of G, then A is called conjugate element of B if for some x belongs to G, this relation holds, the one I'm going to write it over here, that is A equals to x inverse x. This is what a conjugate relation, right? So basically आप क्या कर रहे हो, दो elements को relate कर रहे हो, you are establishing a relationship between two elements in such a way that A is equals to x inverse B x, right? And then in this case A is known as the conjugate of B and B is known as the conjugate of, clear? इसका example आप एक ले सकते हो, वैसे अभी बहुत ज़्यादा उससे समझ में नहीं आएगा कि हम बात क्या कर रहे हैं, right? Although it is very simple to see कि आपके पास यहाँ पे you just write it x belongs to, right? So it is very simple to understand कि आपका एक element है and then you are supposed to take x from any other element G and you are supposed to multiply it with inverse on one side and the element itself on one side and you are going to get the some element, right? So the idea behind this आपको आगे जाके समझ में आएगा. Basically we are going to form conjugate classes, right? And conjugate classes से we can represent basically any group in terms of numbers, right? जब आपके conjugate classes आ जाएंगे तब आप class equation लिख पाओगे, right? So based on that class equation you can identify if what is the kind of this group, ठीक है? अब क्या होगा, this relation is going to be an equivalence relation and an equivalence relation partitions the given group or the set into some classes that are known as equivalency. In this case, those classes are going to be called as conjugate class. Now, let me give you one example. Let's say you have 1, 2, 3 and 1, 3, 2 that belongs to Sn. Okay. Also, I take another element, let's say x equals to 1, 2, right? So when you're going to write it like this, 1, 2, 3, okay, and you're going to multiply it by 1, 2's inverse on one side and 1, 2 here, it is going to give you what? 2, 1, 1, 2, 3, 1, 2, right? And then if you multiply, you're going to get nothing but 1, 3, 2, right? So यहाँ पे these elements are going to be conjugates of each other. Again I'm telling you, अभी यहाँ पे आपको समझ में नहीं आएगा that exactly what we are trying to do. अभी धीरे धीरे पहले हम इस relation को we are going to prove that it is an equivalence and उसके बाद आगे बढ़ेंगे. उसके बाद there is an easier way to calculate conjugate elements in S3, right? क्यों? क्योंकि आपको S3, S4, Sn में क्या होता है, confusion होती है ना? It is a very complicated process to do that. So there is an easier way to do that as well. Also, एक चीज़ आप अभी से दिमाग में रखना, so it becomes a bit easier to comprehend that when we are writing conjugates, ठीक है, so one main idea behind finding conjugate classes or finding conjugate elements for an element is that the order of those elements is always going to be, ठीक है. तो बेसिकली आप कुछ नहीं कर रहे हो, आप एक ग्रुप को डिवाइड कर रहे हो ऑन द बेसिस ऑफ देयर ऑर्डर, द एलिमेंट्स ऑफ देयर ऑर्डर. बस इतनी सी बात है. इस चीज़ को एक बेस बना के चलो एंड देन धीरे धीरे समझ में. क्लियर? ऑल राइट. so that the conjugate relationship, so that the conjugate relation is an equivalence relation okay. First let me remind the let me define the relation. So ARB equals to AB, where A equals to x inverse x, okay, and x belongs to, okay, and A and B are understood that they are elements of आपका group G. Yeah. Now first one is your reflexive, right? Reflexive. So we need that A should be related to A. That means A comma B, A comma A must belong to the, right? Now what is the relation? The relation is, और यहाँ पे you can write as like this as well. Okay, it is denoted by this. Now A relation A equals to implies that A equals to XA x inverse or x inverse AX, right? I can write this simply as A equals to inverse A E, right? So there does exist an element for which A is equals to E inverse A E, right? And E belongs to or, right? So this implies that A congruent to B is reflective, right? Now second part is your symmetric. That means if A is related to B, then B must be related to A, or I should say that if A is congruent to B, then B must be congruent to. Now if A is congruent to B, implies that A equals to x inverse B x, right? ठीक है. I need to, अब यहाँ पे visualize करना ज़रूरी है that what I want from this this proof, right? I want to convert this into such a form that it gets converted to B equals to, let's say, y inverse A y. ये form चाहिए मुझे, तभी I can say that B is also a conjugate to A, right? Now, first of all, I need to isolate B. आपको B चाहिए isolated एक तरफ में, right? That is the hint. So what you're going to do is, you're going to multiply by x on both sides. So xa equals to x inverse b x, xa x inverse equals to eb x inverse. So this is going to be xa x inverse equals to eb, or you can just write b, right? तो आपके पास में ये फॉर्म तो आ गई, बट आई नीड एन इनवर्स हियर एंड द एलिमेंट हियर, राइट? अब देखो ध्यान से, आई कैन राइट इट एज b इक्वल्स टू x इनवर्स का इनवर्स and a and x in, where x inverse belongs to, एलिमेंट ही तो लाना है, राइट? कोई भी एलिमेंट ला सकते हैं हम यहाँ पे, that x inverse here is equals to y. So this implies that b is also a conjugate element too. Hence the given relation is clear. चलो, next up, want to prove that there is a transitive relation, which means if a is congruent to b and b is congruent to, then a must be congruent to, right? So if a and b are congruent to each other, that means a equals to x inverse bx, right? And b is congruent to c, that means there exists another element for which b and c are going to be congruent, right? Now I want to prove the same relation between a and c, right? That means a is equals to z inverse c z. Clear? Now, okay, so I want to eliminate b from here, right? The idea is to eliminate b from here. So can I take the value of b from here and substitute it here? So this implies that a equals to x inverse, what is the value of b? That is y inverse c y x, right? Now if I open this, I'm going to get x inverse, this is x inverse y inverse c y x, right? Right? Now see, I have an element here yx, I need inverse of that here. Can I write it as yx inverse, right? इतना तो अब हमें याद ही है. अगर हम a b का inverse लिखते हैं, so we write it as b inverse a inverse, right? So I can write it at the other way around as well. So this is going to be yx inverse c yx, where yx belongs to, right? Why? Because x and y are elements of G. Now this implies that a is congruent to E. This implies that a comma c belongs to the relation, right? So this implies that the conjugate relation is equivalence in equivalence relation. Then equivalence. Now we'll be writing some properties of it, right? Class, wait a second. First we'll define conjugacy class and then we'll write the properties. Okay? Okay. Okay, what do we mean by a what do we mean by conjugacy class? पहले तो understand that we have defined a relation, that is a conjugate relation, which is an equivalence. So naturally it is going to divide the group into some classes which are going to be known as your equivalence classes or your conjugate, right? So first, let P of A be the conjugate class of A, which is the collection of all elements that are conjugate, right? So this means P of A consists element, let's say x inverse x, where x belongs here. ये क्या है? ये आपका एक एलिमेंट है पूरा, राइट? So C of A, that means your conjugacy class of A is going to consist of all elements which are conjugate to. Now second, if the conjugate relation is an equivalence relation, then it partitions the group in disjoint equivalency classes. That is conjugate classes. And also what is going to happen is that G is going to be equals to the union of CAI, where AI belongs to, right? So G is going to be the union of all the conjugate classes. Clear? All right. Now let's talk about conjugate classes of, let's say, S3. Okay. So how do we calculate, first of all, how do we calculate a conjugate element for the elements in S3? Okay. So just write a note here that let F belongs to Sn such that F sends I to J, okay, and let theta also belongs to Sn, then theta inverse equals to theta of, or we should theta I2. Basically what is happening, what you're supposed to do is, whenever you are calculating the conjugate for any element, right, let's say you are calculating the conjugate for F here, right, and you're taking any theta from Sn group. So what you're supposed to do is simply you just write that theta inverse is going to be equals to the image of 1 under theta 1, then the image of 2 under theta, okay, and then image of 3 under theta, and so on. So this is going to be the answer permutation for you when you are calculating conjugate of an element. For example, why do we do this? First of all, let's understand that. See, let's say F is sending FA is equals to FB, FA is equals to B, okay. So you have given an input, that is your A, and the output is B, both of which are natural numbers because we are dealing in the Sn group, right? Now how is theta F theta inverse going to behave? So what if I give this function the input of theta A, right? So what is it going to happen? What is going to happen is, so theta inverse, theta is going to get eliminated, so I'll be left with theta F of A, right, and this will be nothing but theta of B, right? So basically theta is mapping A to B when I'm applying theta F theta inverse, Basically, if I'm giving the input of theta a, theta is a is also going to be a natural number only, right? Or a number only, or a symbol only. So if I'm starting, I can start the cycle from anywhere, right? अगर आपके पास में if you have 1 2 3 and the images are 3 1 2, ठीक है? So आप कैसा भी cycle यहाँ पे बना सकते हो, right? It does not matter what is the input going to be. तो यहाँ पे theta a is also going to be a number only here. So exactly that is what is going to happen here. For example, let's say I take f belongs to S3 or S5 and f equals to 1 2 3, okay, and there is theta, and the theta is equals to 1 2 4 5, and this will be 5 4 1, okay. So let's say now I want to calculate theta f theta inverse. Now what is the answer going to be here? Simple. I want to write theta f theta inverse, right? And what are the symbols in f that I want the images of? 1 2 and 3, right? So simply I'm just going to replace it by theta 1 theta 2 and theta 3, right? That means the image of 1 under theta, the image of 2 under theta, and image of 3 under theta is going to be the conjugate of this element. And mind you, this is again going to be a 3 cycle here. So this is what theta under the image, and the image of 1 under theta is what? 5, right? Image of 2 4, and image of 3 is what? 1, right? So the conjugate of f, that is 1 2 3, is 5 4 1, right? बस यही है. The main thing is that it is establishing a relation between two elements which are conjugates of each other, and they are going to be of the same order. Clear? It does not matter what you take theta, right? इसका example और अच्छे से you will be able to understand when we will write all conjugacy classes of S3. Okay? Now understand, I want to write conjugacy classes of S3, right? So I'm going to take one element at a time, right? And I'm going to find all the conjugates possible for that element, right? So first, let's say if I'm taking I, okay, and then let's say I'm taking 1 2, and then I'll be taking 1 2, okay. Why? Because I have a slight idea as to the conjugate classes are going to just contain the elements of similar order, right? So I'm just going to take one element of order 2 and one element of order 3, right? 6 का तो exist नहीं करता है इसमें, we know that, right? Now आप या तो C of A लिख सकते हो for conjugacy class, or you can just write like this, okay? This is also a conjugacy class. So from now on we'll be using this notation for this question, okay? So the conjugacy class of I, let's say xi, x inverse is going to be for x belongs to G, right? But since I is identity, right? So this is going to give you what? X inverse, x belongs to G, right? So this implies that E or I is all the only conjugate element for the identity element, right? Now अब आप ऐसे खुद सोचो ना, अगर आप ऑर्डर के टर्म्स में बात कर रहे हो, you are saying conjugacy class is the collection of all the elements of similar order, right? So there is only unique element of order 1 in S3 or any group for that matter. So this means the conjugacy class is only going to contain identity element. Now let's calculate the conjugacy class for 1 2, right? So we need x 1 2, or we can write, let's take theta only here. Theta 1 2 theta inverse, right, where theta belongs to for S3, right? Now what are the elements of S3? We have I 1 2 1 3 and 2 3. Then we have 1 2 3 and 1 3, right? Now see. Now just focus on the calculations, ठीक है, ज़्यादा इधर इधर उधर नहीं कुछ सोचेंगे. We know that this whole expression is going to be equals to what? Theta of 1 and theta of 2. यही किया था हमने, right? And this is going to be the required cycle, right? So now the conjugacy class depends on the value of theta over here, right? सबसे पहले if I take identity, it is going to give me identity or what? See, in identity what happens is 1 maps to 1, 2 maps to 2 and 3 maps to 3, right? So if I am taking the value of theta as identity, what is going to be theta 1? What is going to be theta 1? Theta 1 will be 1 and theta 2 will be 2. This is exactly the element 1, 2. Here. Then if I take the value of, let's say, theta as 1, 3, right? Now what is 1, 3? This is this, right? Now if I'm taking theta as 1, 3, I need the image of 1 under theta, that is 3, right? And then I need image of 2 under theta, that is going to be 2. So this gives me the next next number, next element of S3, that is your 3, 2, right? Now if I take, let's say, theta as, for example, let's say 2, 3, okay? So what is going to happen? 1, 2 and 3. So 2, 3 is 1, 3 and 2, right? Now if the value of theta is equals to 2, 3, I need the image of 1 under theta, so that is going to be 1. And then I need image of 2 under theta, that is going to be 3. See, I have all the distinct 2 order elements of S3 here in the class, right? Now let's take 1, 2. We did not take 1, 2, right? I need, just pay attention here, I need the image of 1 under theta. What is my theta here? 1, 2, right? So image of 1 under theta is going to be 2 and image of 2 under theta is going to be 1, which is nothing but 1, 2 again, right? So this is the same element that is repeating here. Now if I take 1, 2, 3, pay attention. Now if I take 1, 2, 3, 1, 2, 3 means there is a cycle, right? Now I need the image of 1 under theta. 1 under theta, that is going to be what? 2, and image of 2 under theta, that is 3. This is exactly same to 3, 2, right? Then finally if I take 1, 3, 2, again, see, what is happening? 1 is going to 3, 3 is going to 2 and 2 is going to 1, right? I need the image of 1 under theta, that is what? 3, and the image of 2 under theta, that is 1. That is exactly same as 1, 3, right? So it does not matter whatever the value of theta I take. बस यहाँ पे confuse नहीं होना है, ठीक है? Theta 1 and theta 2 are elements only. This is the final cycle that you are getting answer में, ठीक है? So basically it does not matter whatever theta I am taking, the value of theta 1, 2, theta inverse is giving me the distinct elements of order here. Now let's repeat this cycle with a 3 order element, and let's see if we are getting 3 order elements. अभी हमको इतना confirm हो गया है that if I am going to take the conjugacy class for 1, 2, 3, I am going to get 1, 2, 3 and 1, 3, 2 only, right? But we want to verify that if our process is correct or not, right? So the conjugacy class for 1, 2, okay, is theta 1, 2, 3, theta inverse, where theta belongs to S3, right? Now S3's values I'll write here, I 1, 2, 1, 3, then you have 1, 2, and then you have 1, 3, right? Now so now according to our formula, what is the value of the conjugate here? That is going to be theta of 1, theta of 2 and theta of theta belongs to, right? Now what is our theta 1? let's take first theta as 1 2. Okay, now 1 2 में I need image of 1 and 2, right? So what is the image of 1 in 1 2? That is going to be 2. And what is the image of 2 in 1 2? It is 1. Then the image of 3 in 1 2, it is 3. What do I have? 2 1 3, right? Now let's take 2 3. Image of 1 is 1. Image of 2 is 3. Image of 3 is 2. Right? Now let's take another one. Let's take 1 3. Image of 1 is 3. Image of 2 is 2. Image of 3 is 1. Right? Now let's take 1 2 3. The image of 1 is 2. Image of 2 is 3. Image of 3 is 1. And finally we have, let's take 1 3 2 as well. 1 3 2 is going to give me 3 1 and 2, right? Now let's see. 2 1 3, 2 1 3, this is the same value. 1 3 2, 1 3 2, no, 1 3 2 is also same, right? Now 2 3 1, 2 3 1, so these are also same. The only distinct two permutations that I'm getting here is 2 1 3 and 2 3 1, which is the collection of unique 3-order elements and which lie in the conjugacy class of 1 3. So now we can see that whenever we are collecting or we are making the conjugacy classes for S3, you are going to get distinct disjoint sets of elements of similar order and whose union is going to be equals to the group itself. Clear? So now let me erase these. Okay, so now here only two elements are going to be there, that is your 1 2 3 and 1 3 2. Now here G equals to I union conjugacy class of 1 2, then union conjugacy class of 1. Yeah, so this is what we wanted to understand from the conjugacy class. Yeah, okay. Now we have some properties that I would want you to write. Okay, also for homework you do one thing. Homework, find conjugacy classes for S4. ठीक है, S4 के लिए only 24 elements, not a very tedious task, हो जाएगा आराम से, but it is going to give you clarity, right? चलो, now let's write some properties. Properties of conjugacy classes. कॉन्सेप्ट कहीं ना कहीं हल्का फुल्का सिमिलर है आपके कोसेट्स से, राइट? वहाँ पे भी आपके कोसेट्स जो थे वो आपका हर कोसेट वाज नॉट अ ग्रुप और अ सब ग्रुप, राइट? यहाँ पे भी द सेम थिंग इज हैपनिंग. नाउ फर्स्ट वन, राइट, दैट द conjugacy class of identity element is always equals to identity element, right? क्यों? जब भी आप आइडेंटिटी एलिमेंट को किसी भी एलिमेंट से कॉन्जुगेट लिखने की कोशिश करोगे, व्हाट इज गोइंग टू हैपन? ठीक है, तो कॉन्जुगेट एलिमेंट हमेशा आपका सिंगल ही होता है कॉन्जुगेसी क्लास में, ठीक है? देन यू हैव, और यहाँ पे आप डेफिनेशन, ऑलराइट. सेकंड वन इज दैट, ओके, ठीक है, दैट दिस इज नॉट अ वेरी रेलेवेंट पॉइंट, बट ठीक है, विल राइट इट. इफ G is a finite group, then number of distinct elements in CA are given by cardinality of, Then next point is if G is abelian. Okay, let's say you have an abelian group. Okay, you are trying to calculate, or you are trying to find out the conjugacy class for an element that belongs to an abelian, right? So it is going to be of the form xa x inverse, where x belongs to G, right? Now since x belongs to G and a is also an element of G, right? But can I write it as x inverse a? Why? G is abelian, right? G is abelian, so this implies that it is E A x belongs to G. This A belongs A, x belongs to G, where A x belongs to G does not have any relevancy, right? So for an abelian group, what happens is in each conjugacy class there is a singleton element, that is the element, right? Now understand this: if there is an element, if A belongs to ZG, or this we can take afterwards. All right. Now the most important part of this, I guess, conjugacy element ka part aata hai, because this is going to get carry forward to your class equation part, right? So the fourth point is very important. I guess it is the fourth. This is if G is a finite group, then order of C of A, that is cardinality of the conjugacy class of A, is equals to the order of G divided by order of n of A. Basically, the index of the normalizer of A, where NA is the normalizer of . Now, can you decipher something out of it? See, यहाँ पे we are saying the order of centralizer of A. That means the number of elements that are present in the centralizer of any element is going to be equals to the order of G upon order of NA, right? Which is equals to the index of NA in group G. Now we know that NA is a subgroup, right? NA is a normal subgroup. That means basically we are talking about the number of cosets generated by the normalizer of that element is equals to the number of conjugate elements in that class, or it is equals to the order of the conjugacy class. Clear? Now we can write number of elements in C of A is equal to the number of cosets of NA in. Okay. Now we are going to take a proof for this. Pay very close attention to this proof. Why? Because it is going to be somewhat similar to what you will be doing in homomorphism part. Okay. So let E be a finite group, right? And why we are considering finite group? Because index के बारे में we talk about in finite group only. Of A equals to xa x inverse, or x inverse ax, x belongs. Okay. Now we want to show that the cardinality of the conjugacy class of an element is equal to the number of cosets produced by the normalizer of that element, right? So NA equals to x, it contains the element x such that ax is equal, right? Now let T be the collection of all the cosets of, let T be the collection of all the cosets of NA in G, right? Normalizer forms a group, right? And it is a normal subgroup. So that is why we are going to talk about the cosets here, right? So this implies that T equals NA of x belongs to, okay? Now what do we want to prove? To prove that cardinality of T of A equals to cardinality of the number of cosets of NA, right? So now what am I going to do is I am going to define a function, define f from C of A to T. Why? Because I want to show the cardinality of both of these sets equal, right? What am I going to do is I'm going to make a bijection. If I'm able to prove that this function is forming a bijection, that means it is both 1 1 and onto, and we know that if a function is both 1 1 and onto, then the cardinality of the domain and the codomain are both equal to each other, right? So let me define the function. What are the elements in the centralizer of A like? They are x inverse ax equals to NA of, right? So this is what is happening here. यहाँ पे हम elements from the set A उठा रहे हैं, that are those are of the form conjugates of A, that is going to be x inverse ax, and we are mapping them to the coset of that element, right? With the centralizer, with the normalizer, right? Now first step is going to be to prove, or we can take a different color pen, prove, or we can write to show that f is well defined. Now what does showing f is well defined mean? That if I take two inputs to be equal, the outputs are also going to be same, right? That means one input cannot produce two outputs, right? So this implies that x inverse ax equals to y inverse ay. If this is happening, then the outputs of these two elements must be same, right? Now मुझे लेके कहाँ जाना है इनको? Output पे, that means cosets पे, right? So what I'll try to do is I'll try to make cosets on both sides and show them that they are equal, right? So now we can write it as x inverse ax equals to x y inverse ay, right? Side में just write that you want to show, बाद में you can later on erase it, that is na of x is equals to na of y. This you can show by na of x y inverse, right? But in order to show that, I need to show that x y inverse is going to be an element of na, right? मतलब either way आप कर सकते हो, कोई दिक्कत नहीं है, right? Now ax equals to xy inverse ay, right? Can I remove y from here? So this is going to give me axy inverse equals to xy inverse a. So this implies that xy inverse commutes with a. So an element which is commuting with a belongs to na. Now if xy inverse belongs to na, this means the coset generated by xy inverse is going to be equals to na, right? Now na x equals to, if I multiply from y on both the sides, I'm going to get nay. This is equals to function of x inverse equals to function of y, function of x inverse ax equals to function of y inverse a, right? So we have proved that the function is well defined. Now next step is to prove that the function is 1 1. So if I want to prove that the function is 1 1, I will start with two outputs that are going to be same, and I'm going to prove that the inputs are also same, right? So let's say the two outputs are f x a x inverse equals to f of x inverse a x equal to, right? So this is going to be what? This is going to be na of x equals to na of y, right? अब यहाँ से I want to go till x inverse ax and x y inverse ay, right? So what we can do is, if na of x is equals to na of y, what I can write is that xy inverse belongs to na, right? Why? Because HA is equals to HB, that HB inverse belongs to NA, right? So this implies that XY inverse commutes with A, right? Okay. X inverse, Y inverse, X inverse, X, Y inverse, A equals X inverse A, X, Y, X inverse, right? This is going to be Y inverse of A, Y equals to X inverse of A, X, Y inverse of Y. This is Y inverse of A, Y equals X inverse A, X, right? This is exactly what we wanted to prove, that the inputs are also same. Matlab fx1 is equals to fx2 implies that x1 is equals to x2. So this means that the function is 1 1 as, right? Now finally for f is on 2. So f is on 2 is very easy. Kya hai? Just take any element, let y belongs to, let's say, your t, right? Sorry, x. So x is going to be equals to some coset for some element g, right? Where g belongs to the group, right? So what is going to happen? X is equals to fa of na of, so this gives us g inverse of a, right? So this implies that there exists g inverse a for all x belongs to. So hence the range is equals to codomain. That means every element in the codomain has a preeminence, right? So this implies that the function is onto as well. So finally in the concluding part we will write that f is both 1 1 and onto, implies that cardinality of domain equals to cardinality of, right? This implies that cardinality of C of A, cardinality of A, right? Or we can write T here only, write T. Okay? This implies that number of elements in conjugate class of A is equal to the number of cosets of, okay? So this was a very important proof here. Okay? Now one more important, not exactly I would say theorem, but I would say now implication of this theorem is there, right? Let's write that. Okay, this says, this gives you the class equation of the, right? Basically if I give you a very rough idea as to what class equation of a group is, that if I'm writing G here, right? Let's say I'm writing order of G. Okay, and if I'm taking the conjugacy classes, the different conjugacy classes, every whatever there are. Okay, so if you remember, let me take S3 only. So let's say if I'm taking order of S3. Okay, and abhi I just proved. Also I know that the union of all the conjugacy classes equals to the group, right? So can I write that, let's say there is conjugacy class of I, then conjugacy class of I, conjugacy class of 1, 2, and then you have conjugacy class of 1, 2, 3, right? And the union of all these conjugacy classes is equals to the group itself, right? So order of all these groups, order of this group is going to be equal to the collection of or the addition of the conjugacy classes, right? So from here I can write that order of S3 equals to the order of this class plus order of the conjugacy class of 1, 2 plus the order of the conjugacy class of 1, 2, which is nothing but 1 plus 3 plus 2, and this is equals to your C. So basically this is the class equation of any of a group, right? So as many numbers of 1 are going to be there, आपको पता लग जाएगा कि वो element is going to be inside ZG. That is also a different concept, वो देख लेंगे. If an element is going to be inside ZG, क्या होगा उससे? It is going to commute with all the elements, right? And if an element is commuting with all the elements, then what is going to happen to its conjugate? See, सबके साथ commute कर रहा है, अकेला वही element exist. So if I see an equation with, like, let's say this, right? So I can tell the element, the number of elements in the ZG is going to be 1 plus 1, 1, that is 4. So there are 4 elements in a group. If there exists a class equation like this, then there are 4 elements in the ZG. Yeah. Now if there is an abelian group, so for every element the conjugacy class is going to contain only one element, right? That means ZG is equals to G. So एक abelian group का class equation कैसे लिखा जाएगा? Let's say you have Z4. So the class equation is going to be 1 plus 1 plus 1 plus, right? ZG is equals to Z4 only. So class equation. So if अगर कोई ग्रुप है जिसमें आपके 1 plus 1 plus 1 plus 1 ऐसे करके n टाइम्स लिखे हुए हैं इक्वल्स टू द ऑर्डर ऑफ द ग्रुप, दैट मीन्स दैट ग्रुप इज डेफिनेटली abelian. ठीक है, चलो now right, if G is a finite group, okay, then order of G equals to summation of A belongs to G, index of NA. That is, order of G equals to the summation of A belongs to G. What is this? Order of G, order of, right? Now how can we prove it? Very simple proof. आप ये बताओ, हर A के लिए what is this? If I take summation हटा दूँ, if I take a single A, what is it? This is the order of the class of A, the conjugacy class of A, right? And conjugacy classes क्या होती हैं? उनके union, उनका जो union होता है वो G के equal होता है, right? उसी से हम इसको prove कर, right? चलो define a conjugacy relation A related to B such that C of A consists of X inverse, right, where G equals to the union of all of these conjugacy, right? Now we know that, or we let's write it in the expanded form. So G equals to C of A1 union C of A2 union C of A3 union C of AK, where CA1 till CAK are disjoint conjugacy classes, right? यहाँ पे आप एक स्टेटमेंट ऐड कर सकते हो, सिंस द कॉन्जुगेसी रिलेशन इज एन इक्विवेलेंस रिलेशन, इट इज गोइंग टू डिवाइड द ग्रुप इनटू disjoint conjugacy classes, right? यहाँ पे एक लाइन ऐड कर. Now we know that G is equals to summation of or union of all the disjoint conjugacy classes, right? Okay, so from here I can write that order of G equals to order of C of A1, right? Or let me just write that notation. Order of conjugacy class of A1 plus order of conjugacy class of A2, right? Then plus order of conjugacy class of A3 till order of conjugacy class of A3, A6, AK. Now we know that order of C of A or order of conjugacy class of A equals to order of G upon order of NA, right? If I apply the same formula here, what is it going to be? So order of G equals to order of G upon order of NA1 plus order of G upon order of NA2 till order of G divided by order of NA, right? Now order of G again can be written as the index of G under NA 1 plus index of G NA2 till index of G NA, right? In short, I can write what I wanted to prove initially, that order of G equals to the summation of the cosets of different or the indexes of the cosets generated by NA. Yeah. Here, basically this is the class equation, right? So this is the form class equation of first form, right? Now next thing is second form of class equation. Very simple, I'm not going to complicate it here. Okay, order of G equals to ZG plus order of summation of A belongs to G, A belongs to A does not belong to ZG, x of G. Okay, now what does this mean? अगर I जो है सॉरी A जो है वो ZG में नहीं है, that means कुछ different order होगा उसकी क्लास का, conjugacy class का. But if that element is inside ZG, what is the order of the conjugacy class going to be? 1. तो जितने भी elements होंगे ZG में उनका class equation क्या आएगा? Let's say 4 elements, 1 plus 1 plus 1 plus 1, right? And कितने elements हैं? 4. So basically हमने directly यहाँ पे क्या लिख दिया? ZG. Clear? All right. इसको प्रूव भी कर सकते हो आप. कैसे प्रूव करोगे? सिंपल है. सी ऑर्डर ऑफ जी इक्वल्स टू नेशन ए बिलोंग्स टू जेड जी. मतलब मैं बताना चाह रही हूँ कि ये जेड जी कहाँ से आ रहा है. ठीक है, तो आई गेस इट इज गोइंग ऑर्डर ऑफ जेड. ठीक है, तो ए बिलोंग्स टू जेड जी, आई ऑफ एन ए, राइट, प्लस A does not belongs to ZG, I of NA, right? Now, if A belongs to ZG, what is the index going to be? The index is going to be order of G upon order of N of A. Now, since the element is inside ZG, what is the order of NA? It is going to be order of G only, क्योंकि NA क्या होगा? Normalizer of an element is all the elements which are going to commute with G. Now, since G is A is an element of ZG which commutes with all the elements, so the order of NA is going to be order of G only. So from here we are going to get, so this is going to give you order of G divided by order of, right? यहाँ पे just copy this thing here. A belongs to, does not belong to ZG, right? So now what is going to happen? Summation of A, जितनी बार A आएगा उतनी बार, right? So this is going to give you finally order of ZG plus yeah, so this is the second form of the class equation, which is going to be relatively easier for you, right? चलो, some questions I guess I will be taking in the next class. अभी उससे पहले 2 questions I'm going to take which are going to मतलब वो पहले के questions हैं, they are the concepts of our previous classes, and that can be better solved with the now that we have this information. So first of all we are going to do 2 questions and then we are going to take up some examples, maybe not many, 2-3 क्योंकि बहुत ज़्यादा relevance नहीं था. 2-3 questions we are going to take in the next class and then we'll continue with the homomorph, right? So let me just write down the question for you. Okay, so if the question says if order of G equals to p raised to the power n, where p is prime, okay, then the center z equals to e, that is order of z, or this is not z here, zg not equals to identity element, right? That means order of zg is greater than equals to 1. So sorry, greater than 1. If we have a group of order p raised to the power n, okay, where p is a prime number, then you are supposed to prove that zg is not going to be what? Of order 1. That means it is not going to contain one element, it is going to contain more than one element, right? Now see, solve कैसे करेंगे इसे? Order of G equals to ZG or order of ZG, right? Plus summation of A does not belong to ZG, right? Index of NA. Clear? Now see, since NA is NA is a subgroup, right? So this implies that possible orders or we can just write, let me try to simplify it as much as, okay. Acha, understand this, that normalizer of A is not going to be equals to G. Why? Because अगर ऐसा होता है, right, तो ZG is equals to p raised to the power n आ जाएगा, right? अभी फिलहाल we want to prove that ZG, the order of ZG is equals to is just greater than equals to 1, or not equals to, just greater than 1, right? Now understand, since NA is a group, order of NA will divide the order of E. Now this implies that order of NA will divide p raised to the power n, right? Now see, if we are talking about NA, right, and we want to prove that ZG contains more than one element, that is your identity. So consider A does not belong to ZG, right? So if there exists an element that does not belong to ZG, this implies that NA, order of NA to be less than order of G, right? So this implies that order of NA is going to be of the form P raised to the power K, where K is going to be greater than equals to 1 but less than N, right? Now understand that order of G upon order of, or I should write index of GNA equals to order of G upon order of NA, right? So this is going to be of the form P raised to the power N upon P raised to the power K, which is P raised to the power N minus K, right? So we know that whatever the index is going to come, it is going to be divisible by P, right? So this implies that P divides P raised to the power N minus. Also P divides P raised to the power N. This is also true, right? Now what is this? P raised to the power N minus K. This is what? Order of G upon order of NA, right? And this is order of, right? Do we remember the equation that we wrote? That order of G is equals to ZG, or order of ZG, plus summation A does not belong to ZG, order of G upon NA, right? Now we have the values of this and this. That means P is dividing this element and this element, right? So if P is dividing this element and this element, this has to divide ZG as well, right? So I can write that order of ZG equals to order of G minus order of summation order of G upon order of NA when A does not belong to ZG, right? Now P is dividing this and P is dividing this. So this implies that P must divide, order of ZG as well. So if this is happening, then order of ZG must be greater than equal to. This is exactly what we wanted to prove. That means ZG is not equal to identity. That means सिर्फ identity element नहीं है उसके अंदर, it has more than one element. Clear? चलो, let's take today's final question. This is going to be relatively easier. If G is a non-abelian group, of order PQ, where P is prime number, so that order of ZG, right? अब ये आपका क्लास इक्वेशन के बिना भी हो जाएगा, ऐसा कोई दिक्कत नहीं है इसको सॉल्व करने में, right? Now see, we know that ZG is subgroup, right? ZG is subgroup. This implies that order of ZG divides order of P. So this implies that P can be, order of ZG can be, so order of ZG can have values as 1, P, P square and P, right? Now if possible, if possible, order of zg equals to p square. Okay, let's say order of zg is equals to square. Now this implies that wait a second, huh? Order of I guess I here p cube only. Okay, okay, so if this is happening, that means g by zg, we know that it is going to be a quotient group, right? So this implies that order of g upon order of zg, or let's write it like this, is going to be isomorphic, to zp. Why? Because order of g upon order of zg equals to p cube upon p square, right? So this means the order of this factor group is equals to zp, right? So this implies that g is cyclic, or at least it implies that g is abelian, which is a contradiction, right? Now if I take zg's order to be, let's say, p cube, so zg, order of g by zg is going to be what? P cube upon p cube, right? So this implies that g is going to be abelian, right? This implies that this is also not possible. Okay, this implies that we know that order of zg is greater than 1 from where? By previous theorem, right? So this implies that order of zg, right? So आपने 1 p and p square, sorry, 1 p square and p cube तीनों ही आपने reject करे on the basis of what? On the basis of one theorem that we studied before this, where we proved that for any g, whereas g is a finite group, the order of zg is always greater than 1, where the order is of the form p raised to the power n, right? And then it was asked, they were asking us to prove or find out the order of zg, or prove that the order of zg is p, where g is a non-abelian group. Okay, so this implies that the order of zg is equals to, right? All right, so this brings us the end of today's unit. That is your I guess started somewhere in middle only. Okay, fine. So with this we have come to an end of our class equation and conjugacy, conjugate of an element wala part. So from tomorrow onwards we'll take up some examples that I was telling you about, and then we'll be starting with our homomorphism and then followed by isomorphism. Okay, that's all for today. Thank you.